All right, so now we have a formula for a Taylor polynomial of degree n around x equals 0. But what if we want to model a function around a different point, say x equals a? All right, so we want to shift the Taylor polynomial horizontally by a units. Okay, and that's how we're going to come up with a Taylor polynomial around some other point x equals a. So this example 5 is just really, again, sort of developing the concept, but all we're doing is shifting the polynomial by a units left or right. Now in this case, we're modeling f of x equals e to the x near x equals 1. All right, so we want to shift our function to the right by 1 unit. Okay, and here's a polynomial with a horizontal shift of 1, right? This is just a horizontal shift. Horizontal shift to the right by 1 unit. By 1 unit. Okay, that's what that x minus 1 does. We're substituting x minus 1 for x in our polynomial, and that just shifts it to the right by 1. All right, so but we're going to go through the same process, really, as we did before. So let's look at we want the value of the function to match, and we want all of these derivatives to match. So, and we want to find a third degree polynomial. So we want the first, second, and third derivatives to match. All right, so let's first of all look at the derivatives of e to the x. Let's just compute those. And those are super easy to compute, right? Because the derivative of e to the x is e to the x. And we take the derivative of the derivative, and we get e to the x. And we take the derivative of that, and we get e to the x. Okay, so those are really simple. But keep in mind now that we want to model the this e to the x function around 1. So we're interested now in the value of the function and all of its derivatives at 1. Okay, but that's going to be easy too, right? Instead of 0, we're just going to plug in 1, right? So we have e to the 1, which is just e. F double prime, second derivative at 1 is just e. And same way with the third derivative. It's just equal to e at 1, e to the 1. All right, so we have all those derivatives computed. So now we want to go through the polynomials and compute those derivatives, and then match them to the values that we just got for e to the x. Okay, so let's look at this third degree polynomial. We'll call it P3 prime of x. Okay, I'm going to take the derivative of this polynomial that's given up here in the problem statement. So if I do that, again, the constant just becomes 0. I get c1, that's the derivative of c1 times x minus 1 is just going to be c1. And then we have plus 2c2 times x minus 1 plus 3c3 x minus 1 squared. All right. And if we look at P, let's see, where should I put that? Maybe I should write it down here. Let's go write down here. P prime, P3 prime at 1, right? Then again, we have the same phenomena where these higher order terms just become 0, and all we're left with is c1. And we know now that that has to be equal to e, right? Because that's the first derivative at 1 of the function that we're modeling, which is e to the x. All right, so let's keep doing that. So we have, that's the first derivative. Let's match the second derivative. So we need to find the value of the second derivative for this polynomial. Take the derivative of the derivative. We get 2c2 plus 6c3 x minus 1. All right. And so then the second derivative, p double prime of 1 is equal to, again, that higher order term becomes a 0, so it's just 2c2. All right. and that has to be equal to e because we're modeling this e to the x function at 1. All right, so that's going to tell us that C2, let's see, let me run out of room here. C2 has to be e over 2. All right, let's do it one more time. P triple prime of x is equal to, all right, so all we're left with here is 6c3, and then the third derivative at 1 is just equal to 6c3, and that has to match the third derivative at 1 for the original function for e to the x, which is just e. So c3 is equal to e over 6. All right, starting to run out of room here. Let's see if I can squeeze this in. We've got all of this. We got all of the constants. So now we can write the polynomial P3 of x, just by going back to the original kind of generic polynomial up here and substituting those c values that we know now. So we have c0 was e, and then plus e times x minus 1 plus e over 2 times x minus 1 quantity squared plus e over 6 x minus 1 cubed. All right, so there's our third degree Taylor polynomial approximating e to the x about near x equals 1. All right. So the next thing we're going to do is I'll give you the general form of the Taylor polynomial of degree n near a, and then we'll apply it in the last example. All right, so I'll meet you in the next video.